The purpose of this video is to record a little experiment I've done recently about reverse engineering. And the thing I have started to reverse engineer is this old DOS game called Paratrooper. So Paratrooper is a game from 1982. The reason why I picked that game is first that I remember playing this one as a kid. And the second is that it's a very, very simple game. A game for IBM PC. It's made as a clone of this Sabotage game, which was released the year before. And Sabotage was released for a bunch of computers, but not for the IBM PC. And so this clone was kind of popular at the time. And one interesting thing to note is that the guy who wrote this became later a famous mathematician. And when he made that game, he was only 15. So I will not show you where to get that game. I guess you can figure that part out for yourself. But the other pieces of software that I've installed are, on one hand, DOSBox. And so I've installed DOSBox by using Brew because I'm on a Mac. But if you're on Windows or on Linux, you can figure that out. And the other thing that I've been using and that I've also installed with Brew is Cutter. And so Cutter is a reverse engineering platform, which is powered by Reason, which is the actual decompiler. So Cutter is like the IDE and Reason is the software under it. So we'll be using this. And yeah, that's enough to get started. So first, I will just show you this folder that only contains the game that I've downloaded. So I named it para.com and it's only 16K. So it's really, really small. And also it doesn't have any other files. It's just this executable and it just contains everything. So I'm going to run it. So DOSBox dot, the dot will mount the current folder as the C drive, and then para.com. And that starts the game. It displays its own name, then it plays that little tune. And after that, we'll get the instructions for playing, and then I can press spacebar, and here's the game. So it's just like this little turret, which is at the bottom of the screen that I'm controlling with the left and right keys. And then with the up key, I can shoot at the helicopters and the paratroopers. And my goal is to, destroy as many of these things as possible, because if there are too many paratroopers that reach the ground, they will destroy my little turret. Okay, so let's leave this game. That's pretty much all there is to know about it. But still, let's keep in mind the startup sequence. The game displays its own title, then plays a tune, then displays the instructions, and then the game starts. We're only going to look at the very beginning of the execution of that code for now, but it's still interesting to know what we have in front of us. All right, so let's load the thing in Cutter. So the game is here. So I'm typing the name of the game that I'm going to load, and I click open. And so notice that the game is a .com file. If you're not familiar with this, let's say that it's a very, very simple executable from the DOS days. Well, it had equivalents on other platforms, but at least on DOS, the only thing that this is doing is tell the operating system to load that thing in memory and then jump to the beginning of it and start executing the code. So there's absolutely nothing fancy happening here. It's just take that thing from the hard drive or the floppy disk or whatever, put it in memory and run it. So you had a lot more flexibility in the exe files and on modern executables and so on, but the .com file is really as simple as things can be. Okay, so if I click open, Cutter is suggesting that I should let the tool analyze the executable. I'm going to untick that box, and I will show you why in a moment, but let's just say that the tool will get very, very confused if we just let it figure out things. So I also have to help it a bit by going into the advanced options, and I have to just say a few things like the architecture. It's an x86 executable, and it's in the 16-bit format. And then the last thing is the map offset that I set to 100. Okay, so why am I doing this? So since it's just a block of code that will be dumped in memory, there is absolutely no structure in there. There is no header, there is no metadata, there is nothing. So if I'm not telling the decompiler what is in that thing, it will try to guess, and in this case it will get it wrong. So I have to say x86 16 bits. That's the minimum. The other thing is that the convention with COM files is that they are loaded in memory at an offset from the beginning of their segment, which is 100 in hexadecimal, so 256 in decimal. So this is just the convention. That's how it works in DOS. But so if I'm not telling Cutter to use that offset here, then all my addresses will be offset by 100, and that will just make my work of figuring out things more complicated. I can click OK, and the tool starts. So you might have to change a little bit the windows which are displayed. I don't really remember what was the default setup the first time I started the tool, but still what I have here on the left is the disassembly, so you will see all the instructions from my program. What I have on the right is the call graph. I will show you how that works in a moment. On the left you have the list of functions, which is empty because we are only going to discover them as we go. And at the bottom I have the console. And the console is really, really convenient, and that's what I'm going to use most of the time, because with the console you are directly talking to Reason, which is the decompiler that Cutter sits on top of. So Cutter is the GUI, Reason is the actual tool. And so I can type commands in there, and the first one that I'm going to type is S. So all the commands are extremely compact, so you'll have to refer to the documentation if you want to see all the things that you can do with this. I will only use a few of those. But so S stands for seek, and so it simply says, okay, go to that address in memory. Because here you can see that the addresses start at 0000, column 0000. The one on the left of the column is the segment. The one on the right is the offset. So that's how addresses were represented in 16-bit DOS mode, and we'll have to work with this. So I will also get back to this in a moment. So far it just says invalid, 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 simply because, remember, I asked the tool to load the program, to load the game at address 100. So the first 256 bytes are non-initialized, so it's invalid. That's fine. So I will do here seek to 100, and here I am. I can now see that I'm at the address that I requested, and I have instructions that look like instructions. But after a bit, you can see that there is something weird, which is like the same instruction being repeated over and over again. Well, it could be that this is not code, because once again, since I don't have any metadata or any information about the structure of this program, well, it's hard to tell what is code and what is data. You can look at the thing, and if it's code that does not really make sense, then it's probably data. We will have to be careful with this. Because the stuff which comes immediately after kind of looks like code, but if you try to read that code, you'll notice that it doesn't really make sense. Before we get started here, there's just another thing I would like to show, which is that if instead of going to 100, I would have done a seek on FF, which is just one byte before that, this looks like this. And as you can see, I'm still looking at the same range of addresses, but the code has changed. And the reason is that since the tool cannot tell what is code and what is data, it also cannot really say where code starts. And when you have instructions that take several bytes, well, if you're not looking at the right instruction boundary, you can just see something which is like half an instruction and half the next one, and that will not make sense either. So here I really need to know that I'm starting at 100. That thing did not jump back where I want it to go. All right. Oops. Let's go to 0 and let's go back to this. All right. This is also something that you will notice, which is that this GUI tries to follow what the tool is doing, but it sometimes gets a few things wrong. So you will see me from time to time go to view refresh contents to just force the resynchronization between the two. The tool is still in development, so there are a few things that look a bit unfinished, but overall it's great. One thing which is problematic is that series of arrows that you see on the left. I will get back to those in a moment, and I will show you why they are not really working well. But let's first start here by looking at the first instruction that we have at 100. So what does it say? It says mov AX/CS, so it puts the code segment into AX, then it adds something to AX, then it pushes AX, then it does an XOR between AX and AX, so it resets AX to 0, and then it pushes AX again. Okay, so what does that mean? Well, it means that we take the code segment, we add this value to it, then we put it onto the stack. Then we put 0 onto the stack. Then this line takes the data segment, which is the same. So the code segment and data segment were both initialized by the DOS operating system at the time to point at the beginning, or to point at the segment that contains your executable. But so it's also copying this thing into AX, and then we reach retf. So what this all means? And this is important because that's also the reason why automatic analysis of this program usually does not work that well. What we're doing here is that we are calling a retf instruction. And so retf, it's a return far instruction. So I can just look at what this is. So this guy, Félix Cloutier, is someone who's been making a copy of the Intel documentation in a format which is a bit easier to browse. So you will see me use his website frequently. And so the return far, that thing here, well, we could look at all the explanations here, but I will not go into all the details. It's just a return from function call normally. So it will pop an address from the stack and it will jump to it. And so here, what we do, or what the program does, is that it artificially adds an address onto the stack, and then it calls a return. And so return pops the address back out of the stack and jumps there. So it's kind of a weird way to start a program. So instead of jumping to the actual entry point, here we are just pretending to be in a function and returning from it to get to the entry point. Not completely sure why it was done like this, but well, it's not too complicated. Note that I can also click on the first line here, and if I type S, it will tell me what is the current address. I still have it on the prompt anyway. And what I can do is AF, which is analyze function, I think. In other words, it's saying, okay, I'm defining a function entry point where I'm currently at. So AF, enter. And so I need to go to refresh contents. That's one of the things I warned you about. And so now I have one function in my list here. I have the address of that function. And I also have the graph that shows me what this function looks like. So right now you see I only got that little box here that says, okay, here's a piece of code. At the end of it, there is a return. It's nothing very interesting to look at so far, but we are going to figure out where the execution flow goes next. And from that new place, we'll do AF again, and you will see that we'll have something which is a lot more interesting than this. Okay, so what is this? Well, what is this address? So first, I'm pushing this 2C4, which has been added to the code segment onto the stack, followed by 0. And the order in which the address will be defined in that stack is that you push the segment first, and then you push the offset. And so the offset is 0, and the segment is going to be 2C4 plus our current code segment. But so the code segment, if you look at all the addresses here that we have on the left, you can see that the segment is 0 everywhere. I did not ask Cutter to load my executable any particular address, just the offset of 100 that I wanted to have. But so if you were running this from DOS, you would have something in that segment. But here, well, it's just 0. So it's 0 plus 2C4. That's fine. And so 2C4 is going to be a segment, which means that the way that you compute segments in 16-bit DOS, is that you actually have 20 bits of address space, and the segment is the upper 16 bits, and to that you add the offset, which is also 16-bit. So you have 12 bits of overlap. It's a little weird, but so the idea is to, when you want to get a linear address from a segment offset representation, you take the segment, you multiply it by 16, so you left shift it by 4 bits, and then you add the offset, and that gives you an address. So that's what I'm going to do here. So I will do a 2C4, sorry, left shift by 4 bits, so that will be 2C40, plus 0. So let's just go at 2C40 and see what's going on there. So 2C40. There you go. Okay, this looks like code, and normally I should be at the entry point of a function, so I'm going to type AF again. And I will have to refresh the contents. And so here's my function. Now you can see that on the graph side, I have something which is a lot more interesting. So we'll have a look at this in just a moment. But what I would like to show you now is these arrows here. So the arrows here are normally there to show you where branching happens. So when you have a jump, or when you have a function call, when you have a loop and things like this, these arrows will tell you, oh, okay, from here I'm going there, and so on. But then if you look at these arrows, you will notice that they do not point to the right locations in the code. The reason why this happens is apparently that the default font which is used here is either too small or contains some sort of a line offset which is not properly processed by the tool. So if I just zoom on this thing by using wait, how does that work again? Zoom in, yeah, that should be this. Oh, okay, sorry, like this. So if I zoom in, I will reach a point where, for example, that thing here, it's a jump to 2C5F, and so the blue line there, or the blue arrow, goes to 2C5F, and so that's correct. So this one is a jump to 2C6D, and it jumps to 2C6D, that's fine. But if I go back to the default zoom level, which is this, then you can see that all the arrows are offsets, and so I cannot really rely on those. So I'm not going to use this, because anyway, I personally think that the graph view is better. But, well, up to you. At least you know that you have to be careful with the zoom level of that thing on the left. Okay, so what's going on there? First, it's interesting to look at the shape of that thing. So here is my entry point. So it does a few things. We'll figure out what in a moment. But then it ends with a GNE, so jump not equal. And so this GNE can either be true, that will be the green arrow, and it will arrive here, or it can be false, and if it is false, it enters that block here. And so by just looking a little bit at the shape of that thing, we can see that this whole function goes through a bunch of code blocks, but then after a while, there's only one path. I mean, it keeps going this way here, and then there's some interesting branching that happens a bit later on here. But so, yeah, it really looks like it is supposed to go down the green line, because even if it does not go down the green line, it does a few other things, but then it will end up in the green line anyway. Because if I'm taking that part here on the left, if you follow all the arrows, you will see that it's either looping in a few places, so it's looping here, or it's going to loop here. But the only way to get out of that is either by reaching this point, or reaching this point. But this point is also interesting because here what you can see is something which is a dead end. So if you enter that part here, you will never get out of it. And so we'll figure out why. It's kind of interesting. But so let's start with the beginning, and let's see what this thing is doing. First thing it does is that it adds to the AX register the value 11. Okay, so what is the AX register? Well, maybe you remember, but it was in the previous function here, we just copied the data segment into AX. So in AX right now, we have the segment that our program lives in. And here, since we loaded it at the segment 0, ds is 0. So that simplifies things a little bit, because here we know that AX is 0, and so if we add 11 to 0, we have 11, and then we move 11 to ds. So ds is the data segment. And you can see that we are not really going to change ds in a while. I'm not even sure it gets changed at some point, maybe we'll see. But at least for the beginning of our investigation, ds is going to be 11. Okay, that's something to keep in mind. All right, what happens next? We move something into AX and then into ES. The reason why we do that little dance with the register before loading ES is because there is no instruction to directly load a constant into a segment register. So ES is the extended register, can be used for a bunch of things. So in this case, we load 40 in there, and so we have 40 in the extended register. Good. What next? Moving 201 inside dx, and then we do in aldx. Okay, what is in? Well, in, we can look it up on that website as well. In is just about reading from a hardware port. So it's talking to some peripheral. The instruction that we are seeing there is in aldx. So it's reading a byte from an I/O port into AL, and the I/O port is defined by dx. Good. So dx, we just set it to 201. So we are reading 1 byte from port 201. What could that be? Well, let's say thus in port 201. Okay. And what we see here is people talking about game ports, joystick interfacing, game ports, Sidewinder, joystick. Well, we can safely say that this is something that has to do with the joystick, but also notice that we load that byte into AL, and then immediately after, we just replace the whole contents of the A register by something else, which means that whatever we read, we don't really care about. So I don't know in detail, I don't care enough about that thing to really figure it out in detail, but it looks to me like we're just reading something from that joystick port to flush it. But what I know is that we don't care about the joystick at this stage, because we are going to override this. And I don't have a joystick on my computer anyway, so I'm just planning to look at the behavior of the game when I'm using the keyboard as input. So let's ignore that part. What happens next is that we are reading something from an address in memory, putting it in AX. Then we are flipping some bits in there. We're taking a copy of that in DX. This will be relevant later. And finally, we are testing the same bits that we have flipped. And based on the result of that test, we are either going to keep the execution of a function, or we are going to enter that kind of loop on the left. So that is interesting to figure out. We read one word from memory, and based on the contents of that word, we are going to branch. Okay, so what could that be? So first, where in memory do we read that thing? So we see that the offset is hard-coded here, it's 10. And the segment, well, it's ES, and ES was loaded with 40. So it's 40 or 400 because it's a segment plus 10. So 410. And this thing does not depend on the segment that our program is loaded at. So it's just like an absolute address expressed from the beginning of the memory. So for this, we'll need a DOS memory map. So the memory map will tell us where or which range of memory corresponds to what. And so with our address of 410 in hex, with that address we should be able to figure out where or what lives there normally. So we're looking at the real mode address space, which, I mean, I will not go into the details of the difference between real mode and protected mode, but anyway, on the computers, on the old IBM PCs that this game was supposed to run on, there was no protected mode anyway, so it was always real mode. And what it says here is that a typical x86 PC, when it boots up, it will be in real mode. So that's the only thing we should worry about, real mode. Okay, then we have the map here. And we can see that there is some reserved space here, and then there is some usable memory, and then there's some video display memory that's going to be interesting in a moment. And so looking at the start and end addresses, we can see that our address of 410 is inside this block here, which is the BIOS data area. Okay, and the BIOS data area is detailed a little bit here below. And so if we look at 410, we have this here, it's a word, okay, that's what we're reading. It says packed bit flags for detected hardware. So, okay, we're checking what kind of hardware the game is running on, and based on that, we are going to branch, okay? But we are only testing 2 bits in there, because remember, we have this thing here, so we flip 2 bits, and then we test these same 2 bits. Okay, so what lives there? So first we are loading a word, but then we are checking something which is a byte. So we are looking at the lower 8 bits of these flags. And of these lower 8 bits, we are looking at the bits on position 4, 5, and 6. Okay, so it's the highest nibble and the first 2 bits of the highest nibble of the lower byte. So bits 5 and 6. Okay, so what is the purpose of bits 5 and 6? Well, in this page there is a link here to a set of more detailed information about these flags. And so in 410 or in 4010, the bits, well, I said 5 and 6 because I counted from 1, but here they're counting from 0, so it would be these 2 bits, 4 and 5. And so these 2 bits, and I'm looking at AL, so the lower byte. So these 2 bits here, if you do follow that little drawing, you will get to this thing. It's the initial video mode. All right, so the game is checking what the initial video mode is, and it will branch based on that. Okay, so let's keep going. What is the meaning of the value of these 2 bits for the initial video mode? So here I have this little link to int11, which is returning the same information. So we have our bits 5 and 6, 4 and 5 here again, initial video mode. And the initial video mode, 4 and 5, we have this. Okay, there are 4 possible values. Good. So what is this thing doing? Jump not equal will mean, well, it's the same as jump not 0. And test is an instruction that takes 2 values and does a bitwise OR between the 2. And then this means that if the bitwise OR between these 2 things is not 0, we'll keep going. And if it is 0, we'll enter that kind of a special loop. So let's see when we are entering that loop. So we are entering that loop when the result of this test is 0. So it means that the 2 bits were 0, but they've been flipped. So it means that when we read them from memory, the 2 bits were at 1. So if this address in memory contains these 2 bits at 1, we go into this procedure. And the 2 bits at 1 mean we are in monochrome mode. Well, okay, that makes sense, because if we look at the game, we've seen that it was using colors. Well, not a lot of colors, but it was not in black and white. And so at startup, the game checks if it's running, or if the computer has been running black and white mode. And if it's running a black and white mode, well, it's going to do something. Let's figure it out. So I'm running in black and white, so I'm here. Right, so I'm loading this value into SI. And so the SI register is usually the source index. So that's when you want to address memory with an offset inside the segment, you will use the source index as the offset. So we initialize, oops, I did not mean to click on that. Sorry, we are initializing SI with this value, 19F6. And then we get here. So CLD, what does CLD do? Well, it's quite important in this case. So I will go to this web page again, look at CLD. It's important, but it's really simple because it does just one thing. It clears the df flag. So it's one of the processor flags. Okay. And this is hinting at why it's going to be useful, but we'll look at the next instruction to see what's going on. So I've cleared the df flag. df is 0. And after that, I'm doing a load SB with an address and the AL register. So once again, load SB. Load SB. So that's this thing here. So load SB. It says for legacy mode, load bytes, blah, blah. For 64-bit mode, then it does that. Well, we're obviously not running 64-bit mode, so this is what we're getting. So it loads the bytes at address DSSI into AL. Okay. But then if we keep looking at the description of this a little bit, and if I do a find for df, because that's the flag that we just reset, here it says something important, which is that if the df flag is 0, the SI register is incremented. If the df flag is 1, the SI register is decremented. So we've set the df flag to 0, which means that SI will be incremented. And it says here after the transfer. So this instruction here, because we have df to 0, will load a byte from memory and then increment SI. Okay, so first, where are we reading that byte from exactly? We have the offset, SI, but remember the full address is always going to be segment and offset, and so this is the offset, and the segment is DS, and well, DS did not really change, so DS is still 11. So if I want to figure out what this address actually is, well, I can use this little calculator here. Well, by that I mean the console also works as a calculator, and I will say VX, so view as hexadecimal, and I will say 19F6 plus 110, because 110 is 11 times 16. Okay, so 1B06. Okay, so 1B06. Well, let's have a look at it. So seek to 1B06, and then I can do print hexadecimal, and I will display 16 bytes. So what's in there? Well, you can see here on the right the ASCII equivalent of that, and it starts by do you have D, and before that there is a 0D 0A. All right, so we have some string in there. Cool. Let's go back to the function, see what it does after reading that that first character. So it compares the character against 0. And if it is 0, then it will jump here. Okay. If it's not 0, and we can see that here, none of these characters are 0, it will go here. And what does it do here? Well, it sets up two registers, AH, and BH. So AH is E and BH is 0, and then it calls the instruction 10. Sorry, not the instruction, but the interrupt 10. Okay. Well, interrupt 10. We were looking at the documentation for interrupt 11, so let's just look at 10. And we have this. Interrupt 10 is actually a set of functions, and you pick the function you want by setting AH. And so AH is set to E in this case. All right, so E is this one. Write text in teletype mode. So AH is E. AL should be the character that we want to write. And so the character here is in AL. That's what we loaded from memory. Then we have the page number and foreground pixel in the B register, and we've set that to 0. So the default page and no fancy color. So what this thing does, so the little loop that you see here, is that it loads a character, checks if the character is not 0, then it outputs the character, and then it loops. And remember that because of my CLD here, the load SB is incrementing SI. So every time I loop the loop, I will increment the index by 1. And so I'm reading the characters 1 by 1 until I reach 0. In other words, it's a null terminated string. And so a null terminated string, well, if I go back to the address where the string is with seek, I can use PS, which is print string, for a null terminated string. And here I'm able to see the full string, which says, do you have the color graphics monitor adapter? Yes or no? So it's asking the user if the user has a color graphics card. And it is only asking that question if the game detected that the computer was currently running in monochrome mode. Notice that we had two little control code, so 0D and 0A at the beginning. And if we look at this documentation page, we can see that there are 4 characters which are treated as control codes. So we have A and D, that's the one we have there, which are line feed and carriage return. So carriage return is go back to the beginning of the line. Line feed is go to the next line. Let's also notice that we have BS, which is backspace, so erase a character. And then we have bell, which is causing the terminal to emit a little beep. That's really the teletype emulation mode, where you had like an actual physical bell that you could ring on these machines. So what happens after? So once it's done displaying that string, it reached 0, it gets here. And so here, it will call yet another interrupt. So it's .16 this time. All right? 16. This is the keyboard BIOS services. And what is the subfunction that we use there? It's AH0. So 16.0 is wait for key press and read character. Okay, so we are waiting for the user to type something. And so the result when this interrupt returns is that in AH we'll have the keyboard scan code, and in AL we'll have the ASCII character. So let's see what we do with this. Well, here we are going to check AL. So we only care about the ASCII character. And so we check, is it 4E? Well, what is 4E? Well, I can press question mark 0x4E, and Risen will tell me what this maps to. as if it was of different data types. And so I can see here that as a string, it's just the uppercase N letter. So jump equal means that if AL is uppercase N, then I jump here. I jump to this thing. All right. If it's not N, then I'm going to this thing, which is going to test AL against something else. This time it's 6e. So question mark 6e. And I can see that it's lowercase n. And it jumps to the same thing. So if you press N, no matter if your caps lock key is on or not, if you press N, you will end up here. And you can see that here, it's a dead end. So if you say, no, I don't have a color graphics adapter, well, it's not good. We'll see what happens in a moment. But first, if you did not press N, you end up here. And so here we are testing, again, two different values, 59 and 79. So I guess that you know what to expect. So 59 is uppercase Y. And what's the other? 79 is lowercase y. So if you answered yes, I have a color graphics adapter, then you end up here. So you end up in the same location that you would have arrived to if your computer was in graphics mode from the beginning. And if you did not answer yes, then it means that you answered or you typed something which was neither a Y nor an N. So you probably misunderstood the question. So we're going to ask the question again. So we jump here, bloop, and then we just do that loop to print the question again. And we just read another character and so on. Okay, so just for completeness sake, let's look at what happens in this dead end. Well, we move another value into SI, another offset that we're going to read from. And then, well, we can see we clear the thing, we load the bytes one by one, compare them to 0. If it is 0, so if we reach the end of the string, then we are going to loop in place. In other words, when you have an instruction which is jumping to itself, it just means that it's an infinite loop that does nothing. So the program is just stuck there. So the only option you had at the time was to restart your computer. And since the game was supposed to be a PC booter game, well, that was the only way to leave the game anyway. So yeah, you don't have the right graphics card. So out of luck, your only option is to turn the computer off. So if you did not reach the end of the string, then, well, we output the character and then we loop. Notice that there's something interesting here, which is that this thing jumps to the LOD SB instead of jumping to the CLD like this one does. So it's, I mean, it doesn't do any harm, but finding that sort of a little asymmetry in something so simple as printing a string really tells that the game was written in assembly directly. I mean, it's not something that has been compiled. All right, oh, and if we're curious to see what this string is, we can just do this. So view as hexadecimal. So it's 1962 plus this. Okay, so that should be the offsets. And if I jump to that offset and I do a PS, yeah, here we go. So that's the error message you would get if you don't have the right graphics card. Sorry, but Paratrooper does not work on the monochrome display adapter. Notice the little typo in there. You must have a color graphics monitor adapter in order to play this game. Okay. So it was interesting to go through all this, but so far there's very little that we can mess around with. But we are getting to it. Because here there are more interesting things happening. So it starts with something that I don't really understand the purpose of. So if anyone has a suggestion, please let me know. But here we are doing an AND between dx and this mask. And so remember, dx is the register where we store the copy of the thing that we've read in the BIOS flags. So the hardware flags, we flipped 2 bits and then we stored that there. And so what this thing is doing there is that it just clears the 2 bits. So CF is the complement of 30. And so it clears these 2 bits, which also means that it did not matter if we would have taken this before or after doing that XOR. So yeah, that's a little bit odd, but so we clear the bits, and then we set only the higher of these 2 bits. So it means that we are setting, which one was it? It was 11, I think. Yeah. So we only set the higher bit, so that's the one here. So we turn these flags into 8025 color, but then we write those back into the BIOS, and immediately after that, we'll see what this is, but immediately after that we enter graphics mode. So this does not really make sense to me. I don't know why we are changing the text mode before entering graphics mode. There might be a reason, but I'm not aware of it. So yeah, let me know if you know. So what do we do next? Well, this should probably ring a bell if you've been programming old graphics cards. We'll get back to that in a moment. But B800 that we load into the extended segment, is kind of telling. Right after that, we call interrupt 10 with 4 as the low byte of A. Back to interrupt 10. What is this thing doing? So 10. And remember, the subfunction here is the high byte, not the low byte. So here we are putting 4 in the low byte, but so it's 0 in the high byte. So we are entering this one, set video mode. And we pick the mode number 4 in AL. And 4 is this. It's 320 by 200 in 4 colors. So that's like the classic graphics mode of the CGA card. The other cards could do that as well, but they could do a lot more. With CGA, it's pretty much as good as it gets. And this is definitely the resolution and the amount of colors that Paratrooper is working with. So this looks all right. So we're setting that graphics mode. Then after that, we set AH to B, AL to 00, then BX to 10, and then we call interrupt 10 again. All right, so we are calling subfunction B of the interrupt 10. So here, B is the color palettes. All right, so now is the time to look a little bit at what colors on a CGA card are like. So yeah, the CGA card can render 16 different colors, but the trick is that it could usually not display all 16 colors at the same time. There is a trick to do that, some sort of well, at least it could not render 16 different colors in graphics mode. That's the thing. So here we are entering graphic mode, and so after that we are setting a palette, and so the palette is going to be a subset of these colors. So the palettes are documented here. So the graphic mode 320 by 200. There is a higher resolution mode, but it's only monochrome. So here we're initializing the one that runs with 4 colors. And so there's mode 4 and mode 5. So we've seen that the game is in mode 4. And so it has a choice between 2 palettes. And for each palette, there are 2 variants. There is the low intensity and the high intensity variant. Which one does it pick? Well, it sets BX to 0x10. And so 0x10 in BX means that the BH is 0. And so 0 means set the background and border color. And BL, when BH is equal to 0, is going to be a color value. All right, so BL is a color value, and so I can go back to this thing here, and I can see all these colors, 16 colors. But so 16 means that I only need 4 bits, but BL is 8 bits. So is there a purpose to the higher bits? And well, there is a purpose only to the 4th bit, so the first bit of the higher nibble of BL. And unfortunately, it's not documented here. It's not super clear, but well, this is what's happening here, because we are sending 0, so the lower 4 bits are 0, so color 0, and there's a 1 at the top. And the 1 at the top, so that thing which is not well documented, simply chooses or selects the intensity of the palette. So if it's 1, it's going to go with a high intensity palette. If it is 0, it will get a low intensity palette. So I can illustrate this by, well, changing this. So let's try to change that value here. How am I going to do this? Well, I could just use a hexadecimal editor and then change that byte there, but I'm planning to do a lot more things with this program, and I'm planning to do more complicated modifications to it. So instead of using a hex editor, I'm going to write a little program. So don't worry, it's going to be really, really small, and of course, just use whatever you like to write that sort of stuff, but I'm going to use C#. Get rid of that. Yes. Okay, so I will load the file with read all bytes, and it's called para.com. And then I will save it back to the disk to write bytes into para2.com. All right. And between these two things, I'm going to patch the stuff I want. For now, it's only about replacing the value of 1 byte, so I don't really need a program to do that. But as I said, later on, I will need to be a bit more creative with this. So, okay. So I want to change that thing here. And well, for this, I would like to know where it is exactly. And I would also like to know what the instruction looks like exactly. So to see what the instruction is like, I can just print. So if I do, I can also see that here, my move bx10 is at address 2CAE. Okay. And so 2CAE is where I'm currently at here. And the next instruction is in 2CB1. So it means that I have E, F, and 0. It means that the instruction here is 3 bytes. So I'm going to display this px3. I'm going to print 3 bytes from the address that I'm at right now. The instruction here has 1 0 in the first byte and 0 0 in the next byte. And the lower byte is 1 0. So it starts with the lower byte here, and then it follows by the higher byte. So I don't want to change the higher byte, because that would be calling a different part of that function here. That would be selecting the palette. That's not what I'm doing right now. So I want to keep it to 0. So BH remains 0. But BL, which is currently 1 0, I would like to set it to, well, let's say 0 0. And so the thing I want is 2CAF, because that's this one I want. Okay, 2CAF, but that's the trick here. It's going to be 2CAF, but I need to remove my offsets of 100. What did I do? I wanted to say VX. like so. So 2CF minus 100 is 2BAF. And that 2BAF is what I'm going to patch in here. So 2BAF equals 0. So I will run this. That will generate the para2 executable. I will go back to my console, run DOSBox, and say para2. Okay, so let's take screenshots like this, like so. All right, I can leave DOSBox. I can open the screenshot here. And now I can compare that to the result when I am running the original game. And so here, para. And as you can see, the color is definitely different. It's a lot more vibrant in the original game. Nice. So by changing this, I'm changing the intensity of the color, and also the lower nibble is the background color. And so if I leave it at 0, what I have is this. So let's get rid of this. If I leave it at 0, what I have is black. But I can change it to whatever I want. Let's say that's, what if I would set it to 11? And so 11 is B in hexadecimal. And so I could go here and say, turn that into B. Run it. DOSBox, para2, and here we go. Now the background is this beautiful cyan color. Great. Let's keep going a little bit. So this is setting the background color. One thing I forgot to say is that in the palettes that you have here, the palettes are completely fixed except for the background color that you can actually change. And this is what I've just been doing. For the other colors, you don't have the choice between, well, you can just pick between low intensity and high intensity, but that's about it. Next int10 call is this. So we're still calling B, but this time we have 1 on the higher nibble and then 1 on the low nibble. And so what does that mean? Well, here, if it's 1, it means that I'm selecting a color palette, and the palette that I'm picking is 1, so it's using the cyan, magenta, white palette. Okay, well, we could change that to have it run with the green, red, and brown palette. So, same thing. If I want to change that thing here, so it's the 101. If I do VX3, oh, sorry, PX3. PX3. Okay, I can see BB0101. And, well, I know that the lower byte is the one that I want. It's this one here. And so I need to take, so the current address plus 1 minus 100. And it's apparently 2BB7. And so if I change 2BB7 to be, well, instead of being 1, I want it to be 0 to select the other palette. I'm running this again. And then para2. And now this time, the color is the this atrocious green and red and yellow one. So that's what it looks like. well, I don't know if it's the Stockholm Syndrome kicking in, but I think it's not that bad. Anyway, that's going to be all for this time. The last few things that we have here are just initializing DI and BP, which is not related to what's being done here. So the rest is going to be quite interesting, because so far we've only looked at the initialization of the graphics mode, but immediately after that what the game does is that it renders its own title. And so there's a lot of funny things that we can do messing around with that. But yeah, I guess that's already enough for a first video. So I will stop here, and I will eventually continue later on. If you liked it, or if you have suggestions or remarks or corrections, please let me know. Thanks.